Hello and welcome to the second video on function transformations. We're going to determine what happens when we alter a function by adding, subtracting, or multiplying the input by a given number. How does that affect the function's graph? And then algebraically, how does it affect the domain and the range? So notice we're adding or subtracting or multiplying or maybe negating the input only. The output is going to stay the same for these types of transformations. So we're only changing the input, and therefore that's only going to affect the domain, possibly for these types of transformations. The output will remain unchanged, or the range will remain unchanged. So for instance, if we have a function with a finite domain and a finite range, the domain will be affected, the range will be left alone. And again, throughout this discussion, we're going to use the same function we did in the first video on vertical transformations. It's f of x, which is defined by x squared. The domain is the interval from -1 to 2. Right? Notice the range is between 0 and 4. Right? Relative to the y-axis, our graph is only showing up from 0 to 4. For this one, we're going to be affecting what's being plugged into the function. So the input needs to be between -1 and 2. Now, for the original, that means x is going between -1 and 2. We're going to be changing that. We're not going to be putting just x inside the function f. So it's going to be beneficial for us to write that the input, whatever that happens to be, the new input must be between -1 and 2. So for instance, we cannot plug in -3, we cannot plug in 4 to this particular function. Again, that function x squared is being restricted to this domain. Right? Not that we can't square 4 or square -3. It's just for the purposes of this discussion, it's going to be beneficial for us to look at that function restricted to a finite interval. Alright, so let's consider what happens when we add 1 to the input. What does that do to the graph? And then how can we see that algebraically as well? Okay, so looking at the graph, what we're going to do is watch this parameter as c changes between 0 and 1. What do we see happening in the graph? We can see that the graph is being moved to the left by 1 unit. And this is why these inside changes are a little bit more difficult. When you're adding on the inside to x, that makes you think to go right, but we have to do the opposite. We have to go left in this case. Likewise, if we were going to say subtract 2 off from our input before we plugged it into our function, that would have the effect of moving the graph to the right by 2 units. Now, why does that happen? All right, let's see. So you can see it happening in the graph, but let's also explain why that happens. And we can do that by solving a certain inequality. So we know the input must be between -1 and 2 for this particular function. So our new input, though, is not just x, it's x plus 1. So we need to know for what numbers, when I plug them in for x and then add 1, does that result land between -1 and 2? We can solve that and determine that answer by solving this inequality by subtracting 1 from the left, the right, and the middle, and that gives us that x must be between -1 and 2. This right here is the key to this whole understanding of why we're moving left. To solve that inequality, we have to subtract 1. So to find out what numbers x we can plug in, such that when we add 1 to x, it's going to land between -1 and 2, you have to be between -2 and +1. So the new domain for this function is -1, -2, pardon me, to 1. Notice what's happened also. Starting with the original domain, we've taken the endpoints, we've subtracted 1, the opposite of adding 1 to the endpoints to obtain the new domain. Now, what happens when we multiply the input by 3x? What happens to the graph? What happens algebraically? Okay, we're going to look at it graphically first. This time we're letting c range between 1 and 3. Watch the parameter at the top of the graph change between 1 and 3. We can see the graph is being compressed horizontally in towards the y-axis. Each of the points are being moved closer to the y-axis unless you're already on the y-axis, in which case you're staying fixed. 0 times 3 is still going to be 0. Okay, now why is that happening? Again, we need the input to be between -1 and 2. The new input for this function is 3x. To isolate x here, to determine what numbers we're allowed to plug in, we have to solve this inequality for x by dividing by 3. So again, opposite of multiplication, we're going to divide by 3 or equivalently multiply by 1/3. So that's why we say the graph is compressed by a factor of 1/3. Our new domain's negative 1/3 to 2/3. Again, what happened to the endpoints was we divided them by 3 or multiplied them by 1/3 to come up with the new domain. What about when we multiply by a number less than 1, like 1/2? What happens to the graph? Okay, so again, watch the animation parameter. As c ranges between 1 and 1/2, we're seeing the graph is horizontally stretched. It's being pulled away from the y-axis as c's changing between 0 and 1/2. Notice the length of the domain interval also. It was originally 3 units in length. Now it's 6 units in length. Originally between -1 and 2. Now it's between -2 and 4. Okay, so why does that happen? Well, we need in this case 1/2 x to be between -1 and 2. To solve this inequality, we have to divide by 1/2, which is equivalent to multiplying by 2. Right? We have to multiply by the reciprocal. So our new interval, our new domain for this new function is the interval from -2 to 4. All right, notice also the domain length has been doubled. All right, so we went from -1, 2 originally to -2, 4. It's going from an interval of length 3 to an interval of length 6. So we take the endpoints, and instead of multiplying them by 2, we do the opposite. For an inside change, we divide by 2. Lastly, what happens when we negate the graph or negate the input before we plug in to the original function? Well, in this case, if the input's positive, it's going to become negative. If it's negative, it's going to become positive. All right, so what happens to the graph? This is a little bit more abrupt. The graph is being reflected over the y-axis in this case. So again, any point that's negative, any x value that's negative becomes positive. The height on the graph's change is not changing. See, this point 2, 4 is becoming -2, 4. -1, 1 is becoming 1, 1 when we reflect it over the y-axis. Again, why does that happen? Well, this time we need the input -x to be between -1 and 2, which means we have to solve for this inequality for x by negating the left, right, and the middle. And whenever we negate an inequality, both sides, we have to reverse the direction. So the less than or equal to signs are becoming greater than or equal to signs. And this means our new domain is from -2 to 1. So notice we have to do two things when we reflect over the y-axis. We have to negate our endpoints, but then we also have to flip them around. So negating 1 gives us +1. Negating -1 gives us +1. Negating 2 gives us -2. We have to then again flip the endpoints of our domain. So let's make some conclusions here. If you have a positive number, when you add that number to the input, when you add that number inside to x, then that has the effect of shifting the graph to the left c units. If you subtract a given positive number to your input, that moves the graph to the right. Again, the opposite of what you think for inside changes. If you're multiplying a number to the input before you plug it in, if that number happens to be bigger than 1, what you're going to do is horizontally compress the graph by a factor of the reciprocal, 1 over c. And what that means is your graph is going to be pulled closer towards the y-axis, unless you're already on the y-axis, in which case you're going to stay fixed, because if x is 0, then c times 0 is still 0. If your number is between 0 and 1, you're going to horizontally stretch it by a factor of the reciprocal, 1 over c, and that means you're going to pull the points away from the y-axis unless they're already on the y-axis, in which case they stay fixed. Lastly, if you negate your input, that's going to reflect the graph over the y-axis. All right, and the big theme we see in this group of transformations is if you change the inside, you change the input, then that's going to affect the graph in a horizontal fashion. Left, right, compress horizontally, stretch horizontally, or possibly also reflect over the y-axis.